Okay, thanks very much. Thank you, Barbara, for giving me the chance to be here. I'm going to talk about transport in the Earth's core. And of course, I hardly need to justify why transport is important to this audience. These are a number of things why we want to know about the transport properties of Earth core materials. And in particular, one of the things that is determining is the magnetic field. Just a curiosity, this is how the strength of the magnetic field has been developing, has been changed for the past 150 years. So we have a drop. And in fact, we are now monitoring how the magnetic field is evolving very, very closely. So last year, the ESA launched this swarm satellite mission, which is measuring very accurately the magnetic moment and its evolution with time. And this is how it's changing, how it has changed between January and June of this year. You probably can't read these numbers, but just to put this in context, this blue regions here corresponds to a drop of about 0.1%, which in a space of 6 months is not completely negligible. So the properties that we want to look at, and in particular I want to focus on in this talk, are the thermal conductivity and the electrical conductivity of core material. The thermal conductivity is obviously related to convection in the outer core, and the electrical conductivity to ohmic dissipation as the Earth magnetic field is generated. Now, these quantities here have been estimated. There are values. We have had values for these quantities for a long time. And these values came essentially from experiments performed at ambient conditions and then extrapolated all the way to core temperatures and pressures. There are no direct experiments at core conditions, although things may be improving in the future. So the approach that we took 2 or 3 years ago was to use computer simulations for doing this. What do I mean by computer simulations? Well, this is an example of what we do. So we have a number of atoms. So these red spheres are atoms in a box, and then we allow these atoms to move, to interact between themselves, and to move using a computer. And from this movement of these atoms and the interactions, we can extract relevant physical properties, including thermodynamic properties, and in this particular case, also thermal and electrical conductivity. Now, of course, if you want to have something that is meaningful, you have to use the right interactions between the atoms. And if you're talking about atoms and electrons, the only way to get something that is reliable is to use the very basic laws of physics, and in particular quantum mechanics. So quantum mechanics was developed almost a century ago by a number of people, and if you want to apply exact quantum mechanics, then you are hopeless, essentially. So it is impossible to solve the equation of quantum mechanics for a real system. You have to introduce some approximations. So these approximations are now becoming very popular, and a formulation of quantum mechanics known as density functional theory is now being used by a very large number of people. This was introduced about 50 years ago by this gentleman, Walter Kohn, and the idea is that you reformulate the very difficult problem in which you need to know the wave function of the system for every quantum mechanics particle, so for every electron. So this is an horribly complicated mathematical object. You reformulate these problems in terms of the electron density. So in principle, this is an easier problem to put. The caveat and the difficulty still remains in the fact that now the equations are modified and you have an additional term, which is this quantity here. It's called exchange and correlation, and this is where you need to put your approximations. So when you do density functional theory, or maybe you're familiar with the words ab initio or first principle simulations, you are always dealing with an approximated quantum mechanics method, and this is where the approximations go in. For the electrical conductivity, in the language of density functional theory, this is the expression that you need to compute. Now, I'm sorry to inflict this horrible mathematical formula upon you. I promise I just have one and another transparencies on this. So you don't need to, you're not really required to look at much of this formula. The only relevant quantity that you want to look at is this object here. So we are talking about electron transport, and so what we want is to compute essentially the expectation value of the momentum operator. And the momentum operator in quantum mechanics is the gradient. So this is why you have these matrix elements of the gradient. And these quantities here, this size, these are the electronic wave functions. There is a little caveat about what exactly these wave functions mean within density functional theory, but we can leave it aside for the time being. This is the formula that gives you the electrical conductivity within this formulation. Now, in fact, it gives you the optical conductivity. Okay, so this is the conductivity as a function of frequency. This particular formula is for a snapshot for a particular set of positions of your atoms. If you're looking at evaluating the conductivity of a high temperature solid or of a liquid, what you need to do is to sample your phase space. So you need to generate snapshots which are representative of your high temperature system. So you will do that, and then you take the thermal average of this quantity, and this gives you the optical conductivity at finite frequency. The electrical conductivity then is just the limit for omega going to 0 of this object. The electrical conductivity has a similar formula, which we don't need to discuss, and that's because essentially electronic transport is as the thermal electronic transport has essentially the same origin as electrical transport. But for the thermal conductivity, for the total thermal conductivity, you also have an ionic component. Okay, so heat is also transported by ionic vibrations. These ionic vibrations are of course, very important if you have an insulating material, but for a metal like iron, they are a very small part of the total. In fact, for iron, this quantity here is only a few % of the total thermal conductivity, so it can be safely ignored. Right, now I want to show you in practice an example of how you actually apply this theory for a real system. And the first system I want to look at is a system for which we know very well the conductivity, so that we can compare with experiments. So this is liquid sodium at ambient pressure and just above the melting temperature. So there are no uncertainties here. We know exactly what the electrical conductivity is. What I'm plotting here is this optical conductivity as a function of frequency. And you can see a number of lines here, a number of curves in this graph. And these are curves which are obtained from calculations performed with simulation cells that contain a different number of atoms. And so you can see that for this particular case, you need to use, before you converge your values, you need to use a very large simulation cell. So you need to use a simulation cell which contains at least 1,000 atoms. Otherwise, you underestimate your conductivity. How does it compare with experiments? Well, this is the result for the electrical conductivity compared with the experiments. This is the thermal conductivity, and this is the Lorentz parameter. Okay, so the Lorentz parameter is the ratio between the thermal and the electrical conductivity, and also divided by the temperature. So the agreement is quite respectable, and it gives you confidence that the methods are doing what we would like them to do. So the next thing is to try to ground truth our calculations of iron again in the region where we have undisputed values. And this would be iron at low pressure. Now, I know I don't have to leave this podium, so but I want to draw something on the board. I'll be back in 30 seconds. So if I plot now the resistivity, okay, resistivity is the inverse of the conductivity as a function of temperature. for a standard material, what we expect is that this behaves in this way. So you have a straight line, at least in the low temperature region. Now, if you look at the conductivity of the to the resistivity of iron, this is what it looks like. So it's a kind of parabola. It's nothing like a straight line, but it becomes a straight line after the Curie temperature. Why do you have this behavior? Well, the reason is because iron is a magnetic system. So when you are at low temperature, you have all these spins aligned, and as you increase the temperature, you start getting some excitations in the directions of the spins, and this spin disorder is itself causing collisions with the electrons that travel. So it is increasing the resistivity itself. And so the more you increase the temperature, the more disorder you get in the spins, and so this spin component, if you like, to the resistivity is increasing with temperature. So this is what the spin component will look like, this curve down here. Now, when you reach the Curie point, the spins are completely disordered, and so the contribution due to this effect does not increase anymore. It stays constant. So this is what it looks like. And the conductivity and the resistivity only increases linearly as in a normal material. In fact, I will come back to this linear increase with temperature towards the end of the talk, because this is also crucial for understanding the Earth's core. Now, what we calculate with this method that I showed you before are just the resistivity due to the vibrations, to the lattice vibration. We miss this term here. So if we want to compare to iron at low pressure, then we have to compare to this value here. And this is what the comparison looks like. So again, here you have the total resistivity up here, and the lattice component of the resistivity down here. And these are the results of the resistivity computed with different simulation cell sizes. And so you see that you need to include simulation cell sizes with, in this particular case, at least 250 atoms or so. And also, this is another technical point you don't really need to know, but you need to use a large number of K points. So again, this method seems to produce results which are agreeing with experiments where we have experiments, and now we want to use it for the conductivity of the material at Earth's core conditions. But what are Earth's core conditions? We are trying to do this in a self-consistent, self-contained way. So what we would like to do is to determine the core conditions within this theory. And so we have to determine what is the temperature profile in the core, and also what is the composition, because the composition is going to affect the conductivities. Now the temperature, of course, the first shot at the temperature is to assume that the core is pure iron, and then look at the melting temperature of iron in core boundary conditions. This will provide the first constraint on the temperature of the core, and then we'll move on from that. The way we do these calculations is by evaluating the free energy of the solid and the liquid, in this case solid and liquid iron. There are standard statistical mechanics methods which allow you to do this, and also within first principles calculations, which I'm not going to discuss because it will take too long. But basically, this is something that you can do. So you compute the free energy of the solid, the free energy of the liquid, and the points where they are equal gives you the melting temperature by definition. Once you have the free energy, in fact, you can also do something else. You can compute other thermodynamic properties and compare with experiments where they are available. For example, we can look at the eugonio of iron. This is the pressure volume equation of state, and the points are the dots obtained from experiments. The lines are what you get from density functional theory. And here on the right is the speed of sound as a function of pressure. Of course, you have the solid here, and then you have a discontinuity here, and then the liquid. what I'm comparing here with first principle calculations are the calculations for the liquid. And you can see that the agreement is quite respectable. And from this, you get the melting curve. So this is temperature as a function of pressure. The inner core boundary is up here, 330 GPa. The curve that we calculate is this black continuous line and this dashed continuous line. If you want, this is the kind of representative of the error bar in the calculations. There are, a very large number of groups that have attempted to compute the melting temperature of iron or measure the melting temperature of iron. It's impossible to include them all, so I apologize if not everybody is present on this list. But the point that I want to make is that if you look at the very latest diamond anvil cell experiments, the Anzelin et al. Appeared last year in a paper last year. These are in very good agreement with this density functional theory calculations, and therefore they support, once again, the reliability of these methods to predict the properties of iron at core conditions. What about composition? We know that we must have some light impurities. The way we approach this problem is again combining thermodynamics and seismology. We look at the inner core boundary here, where we know that there is a density change, density discontinuity, because of the solid-liquid transition. Now, this discontinuity is between 5 and 6.5%. We still have a relatively large error bar on this number, and this will affect necessarily our conclusions. But these numbers is a lot higher than the density discontinuity that you get from the melting of pure iron. So a lot of this discontinuity is actually due to partitioning of light elements between the inner core and the outer core. If we are at equilibrium here, now again we exploit thermodynamics, which tells you that the chemical potential of elements which are in thermodynamic equilibrium have to be the same in the solid region and in the liquid region. So this is expressed by this quantity here. And by computing these chemical potentials of candidate light impurities, we can work out what is the relative concentration of these impurities between the liquid and the solid, or if you like, the partition coefficient. Now, the way we compute this, there are some formulas here. I'm just going to tell you this in words. Is effectively, this is what we do. We take, this is a simulation which represents pure iron. We take one of the atoms here and we transmute it into an oxygen atom. So it's an alchemical transmutation. You may argue that no such thing exists in reality, but in fact you do have some alchemical transformations when you have nuclear reactions. But in any case, this is a very well-defined mathematical process that you can carry out in a computer. And what you do during this transmutation, you compute the reversible work. The reversible work is identical to the difference in chemical potential between this impurity and iron. And once you have the information on the chemical potentials of this impurity, you can use them to work out a density, a composition, a likely composition of the core. And this is what we come up with. So we looked at the moment, only these three impurities. We're actually planning to look at other impurities like hydrogen and carbon, but we haven't done that yet. But looking at these impurities here, which seems to be the most fashionable anyway, we come up with a distribution which has about 8% of either sulfur or silicon in the solid core, and a similar amount in the liquid, so there is very little partitioning of sulfur or silicon. And then oxygen that would go completely in the liquid. There is oxygen turns out to be incompatible in the solid, essentially because of its very small size compared to iron. This difference here, 8 to 13%, is because of this uncertainty that we have on the density jump at the inner core boundaries. So depending on what density jump you take, you would get one or the other. Actually, I have to say here that to avoid confusion, that these are mole percent, okay, not weight percent. So there's always the danger that we misunderstand what we're meaning with these percentages here. Now, this partitioning of oxygen between the solid and the liquid is also responsible for a change in melting temperature, and in particular the pressure in melting temperature compared to the melting temperature of pure iron, and it's not completely negligible. You can see it's almost 1,000 degrees. So we come up in the end with that kind of temperature profile. So a temperature at the bottom of the core, at the bottom of the outer core of about 5,500 degrees or so, and then if we assume, as most people do, that the outer core is in a well-mixed state, so the temperature profile should be adiabatic, we can also work out what the temperature is at the top of the core. So basically, we have a temperature profile, which is plotted down here. So this is pressure, outer core, inner core, and the temperature increases as you go deeper and deeper. This line here, this band here that you see actually is the temperature profile, likely temperature profile, which results from these calculations on the melting of iron and the likely amount of light impurities in the core. This black line is the temperature profile that you would have if the core was pure iron. I'm plotting here now the thermal conductivities, and again you get these values here, this green line, this with a band, depending on exactly what temperature and composition you take. And the first thing I want to say is that if you compare this with what was used before, these values that were used before, you have a large increase, so at least a factor of 2 or 3 increase compared to previous values. This black line is the conductivity that you would get if the core was pure iron, and here now we are also comparing with other independent first principle calculations that also produce essentially the same results. And more recently we also had some experiments being performed, and which are being performed actually at the moment, which also agree, well, also support these high values of conductivity. So this point here, these blue points here are, and also these open diamonds and open squares are from this recent experimental paper. But what is it so different in these experiments that is producing these values of conductivity which are so much higher than before? Well, what they have done in this paper in particular is to look at this problem again. So this dependence of conductivity as a function of temperature. So why do you have this linear increase of conductivity, of resistivity with temperature? That's because the mean free path of the electrons decreases with temperature. And so you have more collisions, and the system, the resistivity increases. However, this mean free path can only decrease up to a point. So up to a point in which the length of the mean free path is roughly equal to the spacing between the atoms in the system. And this causes a saturation effect. The saturation effect, in fact, is not new. It has been known for a very long time, but has never been applied to core material. And that's the reasoning behind this experimental paper in which they say that they introducing this saturation effect, they obtain a much higher conductivity, so much lower resistivity, so much higher conductivity. And we do indeed see this saturation effect. So you see a low temperature, this is almost linear, but then as you increase the temperature, this resistivity is curving. So this saturation effect is actually showing up. Now, before I leave you, just a couple of final transparencies on some ionic transport. From these simulations, you can also calculate almost as a byproduct things like diffusion coefficient, in particular in this case. So what you do, you have your positions of the atoms in your system, and you see how they vary with time. So you can construct a quantity that is called mean square displacement, and And if you plot this mean square displacement, you obtain this kind of straight line behavior in the long time limit. The derivative of this quantity here is equal to the diffusion coefficient. In fact, there is also an alternative and a completely independent way of calculating it from the autocorrelation function of the velocity. So if you take the velocity, so you correlate, you compute the autocorrelation function, and then you integrate it, you obtain the same quantity. In this graph here, you can see the two quantities, this diffusion coefficient calculated using these two different methods, and of course they give you the same answer as they should. It's nice to have two different independent but equivalent methods to compute the same thing, because then you can cross-check your calculations. So down here you can see plotted the actual diffusion coefficient for iron, oxygen, and silicon on the outer core adiabat. And so you go outer core, inner core here. This is down here is iron and silicon. I have a very similar diffusion coefficient. Oxygen is diffusing faster, about factor 2 or 3 faster. And there is a little bit of dependence on pressure and temperature, of course. Temperature is also increasing here, but not a huge difference. And finally, you can compute the viscosity. Viscosity, again, can be computed using Green-Kubo relations. In this case, is the autocorrelation function of the off-diagonal components of the stress tensor. It's this quantity here. So this is the autocorrelation function is plotted down here, so it's going down like that. You integrate it, and you obtain your viscosity. So this is, again, plotted for the outer core, inner core boundary, and you can see how it varies for a different system, actually. So the black lines are for a pure iron system, and red and green are for two systems with two different compositions in terms of amount of light impurities. And you can see there is a slight variation, about factor of 2, as you go from the top of the core to the bottom of the core. Okay, so this brings me to the conclusions, which are that the main conclusion from the work is that we find conductivities that are significantly higher than what had been used before. And this has a number of consequences for the Earth. Particularly, the power for the geodynamo now is greatly reduced, because you are essentially wasting a lot of heat to conduction along the adiabat. So you need to compensate for that, and maybe you can do that by having a more rapid secular cooling, but the consequence of that could be that we have a younger inner core than previously thought. And also, we may have a situation in which the top of the core may be thermally stratified, as this is illustrated by this figure produced by Bruce Buffett in his news and views on this paper. And yeah, I just want to finish with the credits to collaborators. Monica Pozza at UCL, who did most of this the DFT calculations, and then Chris Davis and David Gubbins, who helped us put everything up together within the geophysical context. That's it.